I think no, this should be the same one. Did we do a study plan last time we had a meeting? Yes.
Yeah.
Okay, let me double check my records. So,
Yeah, I got an email saying I need. That's how I got this.
yeah,
Switch it.
right. Yeah, let me check my records and see, because they, yeah, we kind of removed those in. You shouldn't, so let me check it and yeah, let me send me an email just to remind me. Yeah.
Alright, thank you.
I have an advising question.
Sure.
So. I'm asking you to.
Yes, I think I would give them, yeah, maybe middle of December, that's when they're finishing up with all the courses. If they need official confirmation, so I don't think it's gonna show up on your transcript for a couple of weeks, because it takes a while for the grades to process. But if you need something sooner than that, we can give you basically a letter of confirmation. So if you send me an email that you need, like, my employer needs to verify, then we can send. Basically, I can give you just a PDF with the official letterhead, say that, Simon finished all this stuff here. It's still processing by the school, but he's basically all done. So,
Okay, so I just send you an email.
yeah.
Okay.
Yeah. But you should, but most employers don't verify the exact date. So I think if as long as you say like middle of December, that's.
Okay.
That's
So there's one. That was the issue date or the last day.
the last day finals is this one, because that's when you're.
If I ever needed.
Yes. Yeah. Mhm.
I got scared and I let off the throttle. I hit the brakes. I'm like, that car up ahead is coming by. It's coming really fast. Yeah. That was the thought process. And I was like, so at least 150, I might have maxed it out, but I couldn't go to the end. I didn't look down. I think it was like, I am terrified. Like, I'll cruise at like 120, 130, but like as soon as I got up there, dude, I was like, this is easy church. So at least 150 is what I'm saying, because that's the last number. Still pretty fucking fast considering I was the top out of my 160. Most of the way there. But I was like, I saw an empty stretch and I was like, dude, it was so good. Because I told you it was like the first time in like a month.
Oh, yeah.
I was getting the upshift on it, so I was getting the Excel pop, the decel pop, and everything, bro. Fucking yes, nigga. I was like those noise, the fucking the noises and the rich. Like I was like really on it too. So like when I was like, I just went over, so like downshift into like gears, like when I can pass around, I'll just fucking take off. So like I was, I was playing in a power band instead of just cruising in 600 way. So like 2 years, I was fucking. I just thought it was.
Yeah, it's. You have to click the surface and unplay. I guess you get a five.
It's 5:30. Let's go ahead and get started. Right, good afternoon, or I guess good evening, everyone. How's everyone doing today? Good, doing good. All right, so the plan for today, and basically we're gonna be doing this all the way up until Thanksgiving, is we're gonna be talking about theory in finite element. Okay. So I will kind of preface this by saying that almost universally, this is probably everyone's least favorite part of the class. That's why I get comments on it every year. And the primary reason is because it's not answers, and we're not going to see answers for about a month. Well, you guys will for your midterm projects, but in the class we're going to take a break. But we have to go through this because technically this course is not an answer course. We have to cover the theory behind finite elements, just so that you kind of know what you're doing. So I know it's going to be a lot of math. It's going to be a lot of more hand calculations. I think you want to do in this class. But we got to do it. Okay, so we have to kind of go through this, and 1 month honestly is pretty generous. And so for a lot of other finite element courses, this is either going to take up the entire class or it's going to take up 80–90% of the class. I know when I learned finite elements for the first time, basically my first 3 courses in finite elements were all like, so it's all just hand calculations, theory, math, and we didn't really get to touch a software until pretty so. So we're doing about 4 or 5 weeks, and so not so bad in the grand scheme of things, but I know it's not the most fun portion, but I'm gonna try to make it as fun and interesting as I can. Okay, so some announcements. Remember, activity 4 is out there. So activity 4 it's a long one, and so if you were here last Thursday, you know that we were kind of working all the way up until the end. And there were kind of various issues that kind of popped up, as usually happens during activity 4. So if you're having issues with activity 4, or you're getting you're not getting the results that you need to, you're running into some errors, let me know. And so I'm just happy to help. I think activity 4 is due next week. You have a bit more time for activity. Okay, I think that's all my announcements. Activity 4 will be the last assignment that's due before the midterm project. So once kind of I know some people kind of started the midterm project already, but once activity 4 is in, then the only thing I'm having you guys work on is just the bit. All right, any questions on anything before we get started for today? Okay, all right, so let's go ahead and get started. Can I post the lecture video from last Thursday? Oh, is it not posted? I'm sorry about that. Yeah, I'll post that when I get back. I uploaded it on YouTube. I just probably just forgot to post it. Yeah, thanks for catching me. I think that's 2 weeks in a row now, so apologize for that. Okay. All right, so the lecture today is something called the direct stiffness method. And so the idea behind the direct stiffness method and kind of the idea behind finite element theory in general, or at least what we're going to cover in this class, is to give you guys a sense of kind of what ANSYS is doing underneath the hood. Okay, because I really don't want you guys to leave this class with a sense of like, you know how to use ANSYS, but with regards to what ANSYS is doing, kind of when you after you apply the boundary conditions to the mesh, I don't want you guys to think that that's some kind of magic box that just kind of magically solves things. Okay? There's actually some real engineering that goes on there, real computations. And even though we're not going to be able to get into kind of the really how to implement a software like ANSYS, you should at least have a sense of what's going on in terms of that's kind of the motivation here. And so, in terms of exact practicality, the direct stiffness method, it was kind of developed fairly early on in the history of finite elements. And so at this point, a modern software like ANSYS is not going to use the direct stiffness method, at least not entirely, but at least the same methodology and the same the same kind of mindset, the same kind of setup, the same kind of steps. ANSYS uses. It's just the details of these steps is very. So the direct stiffness method. What I'm going to say is that the direct stiffness method serves to illustrate the essential steps in computing a finite element. So what you'll see over the course of the next few weeks is that, when I mentioned the finite element method or finite element computations, there's a set kind of algorithm or set recipe that we follow. The exact details of each of the steps is going to be different in a more modern software, but we generally follow the same steps. Okay. And so that's kind of what I mean by the statements that we're going to learn the direct stiffness method, even though the direct stiffness method is not, directly used. The same steps still apply, the same overall steps. And so if you ever get a chance to look into the source code for ANSYS or any of the other kind of modern softwares, it's not going to be, it's not going to follow the exact details of what we're going to go over. In fact, they've actually made it a lot more complex. But the same general steps are still going to. And so let's go ahead and name those general steps. And so, at this time, these steps are not really going to mean much. But throughout the course of today's lecture as well as Thursday's lecture, we'll kind of illustrate each of these steps and what they generally mean. So this procedure here is going to be different than kind of the step-by-step process we've gone through before. Okay, and so I want to differentiate between the two because we've already kind of gone through, or we've gone over kind of a step-by-step process of how to produce an FEA solution through ANSYS, right? So that was getting your geometry, assigning the material properties, meshing, boundary conditions, solution, right? So that's separate. And so, this is a different methodology in terms of if you were to compute it from scratch, what steps would you go through? Okay. And so the first step is to discretize your geometry and label the nodes and elements. The key step there being labeled, right? And so in all the calculations that we're going to do over the next couple of weeks, you don't have to worry about meshing. I'm essentially going to do that for you, but you do, have to worry about how everything is labeled, how all the elements are labeled, how all the nodes are labeled, because that's going to affect how we do the rest of the steps. Number two. Step two, so once you've labeled all the nodes and elements, step two is to compute something called an element stiffness matrix for every element. Well, that's going to be the topic of today's lecture, or a big chunk of today's lecture is talking about what the element stiffness matrix is, how do we compute it, and what exactly does it represent. Step three is a step I like to call assembly. And so when I say assemble, what I mean assemble all Step three is to assemble all the element stiffness matrices into a global system. Okay. So I think we'll probably get to that today as well. Step four is to apply boundary conditions. So what the boundary conditions are going to do is that they're going to modify our global linear system. Okay. Last step is we're going to solve our global linear system. Okay. Because what we're going to get at the end of step four is a very large system of linear equations. Okay. So we're going to have maybe 3 or 4 unknowns, and we're going to have 3 or 4 equations that we can use to solve for those unknowns. Okay. So step 5 is to basically perform what's called a linear solve. So you're solving just a system of linear. All right, and so like I said, the focus of today's lecture is going to be primarily these 2 steps. And if we have time today, we'll get to the boundary conditions as well. All right, but I realize that writing these steps down right now they mean absolutely nothing just because it's just a lot of jargon. But you know, by the time we kind of get to the end of the next two lectures, you should understand every step. And then basically every single one of these problems are going to follow. Okay. All right. Any questions on this so far? Okay. All right, so let's talk about the stiffness functions. Let's talk about what it is and what it represents, and more importantly, how do we compute that? All right, so to start us off, you know, I want to kind of motivate this discussion through hopefully something that everyone already knows. Let's look at Hooke's law for springs. Let's take a very simple spring system. So let's have a fixed wall, have a spring attached to that wall. And so what we know about springs is that if we apply a force to the spring, so let's say that we apply a tensile force, so we're going to pull on the spring to the right. What's going to happen is that this spring is going to stretch, okay? And it's going to stretch until the internal forces or the internal tension within the spring equilibrates with that external force. If we apply a tensile force, the spring is going to stretch longer. Okay. And the amount that it gets longer, and so let's say that the original configuration of the spring is something like this. Okay. And so in purple there I have the original configuration of the spring. And so the amount that the spring stretches, we call that D. Where D here is, you know, it can be deformation, it can be displacement, it can be, I'll call it displacement. So the D is a measure of how much the spring is stretching after you apply external force. All right. And so what Hooke's law basically says that if we have a situation like this, then the amount of deformation that we see is closely related to the amount of force that we apply. Okay. And so Hooke's law is actually a very simple equation. F is equal to. Okay, on the other side of the equal sign, we'll have the displacement D. Okay. And kind of modulating these two, you know, very similar to our linear elastic equation, is we have a proportionality constant K. Okay. Where K is the spring constant for the spring. So usually we label each spring with its spring constant above it, like that. That's Hooke's law. So Hooke's law basically says that if you have a spring with a certain spring constant and you apply a certain force, then you're going to see a deformation, and that entire phenomenon or that entire relationship is summed up with this equation. Okay. So very simple equation. So hopefully it's one that you've seen many times before in other classes. But we can take this equation and kind of take this, or I say kind of take the idea of this equation and kind of generalize it to kind of more general systems. Okay. Because we have three terms here, but you know, you can see that we can draw kind of a lot of you know, a lot of comparisons to other types of systems. Okay. Okay. And so let's take each term in this equation here and let's actually kind of examine or talk about kind of what that term kind of represents in general. Okay, so let's start with the F. And so from our figure above, we see that the F that we're applying is some kind of external force, right? So it's some force that we're applying externally from the spring. Okay. if we generalize that concept, you know, to just any kind of external effects, right? What is something that we've kind of used in this class already that kind of represents external effects? Boundary conditions, right? And so this F here is kind of a representation of boundary conditions, or just any kind of external effects that can be applied to a physical system. Let's go from left to right. So let's talk about K here. K is our spring constant. And so the spring constant, what that represents, it represents kind of the strength of the spring, okay? Another way that we can describe the spring constant is that it's a property of the spring itself, kind of innate to the spring, and it modulates how the spring responds to external stimuli. And so that sounds very similar to something that we've covered in class already too. This is basically a material property of the spring. And I would even go so far as to throw geometric properties in there as well. And so the K there, you know, one way to kind of generalize it is that's kind of the material and geometric properties of our physical system. Okay. So we go ahead and write this material slash geometry. Because the geometry is going to affect your response as well. Okay. If that's so, geometry is not something we've played with all too much in class. We did a little bit of it in activity 3, where I think what a lot of people did in activity 3 was they made the posts thicker, or they modified the geometry in order to meet the design requirements. Okay, but geometry absolutely has an effect on our response. Okay. All right, and then finally we get to. So the D is represents, at least in the spring case, it represents how much the spring is going to deform, or how much it's going to displace in response to the load. And I wrote that kind of very intentionally, right? And so, you know, I think kind of when you're first learning about springs, you kind of see it as all kind of one instantaneous process, right? And so if you have a force on a applying a spring, and then it's going to deform. But I wrote it like this just to say that, you know, you can think of the deformation as kind of the system's way of responding to an external stimulus. Okay, so it's almost like a call and response kind of have a spring by itself. If you apply no boundary conditions to it, it's just going to be a passive spring. It's not going to do anything. It's not until you apply some kind of external stimulus that's when you get some kind of response. Okay, and that response is represented by the deformation. Okay. And so to generalize this, you know, this is you can kind of almost think of it as kind of the physical response of a physical. You can almost think of it like the response of a physical system to any kind of external effects. Okay. If you have any physical system, if you stimulate it to a certain degree, right? So if I take that chair and just kick it across the room, you know, it's going to respond, right? And so, you know, this kind of a central kind of concept of finite elements is that by some kind of external effects, you apply boundary conditions, your system's going to respond. And then how the system responds, you know, exactly how much deformation that you get, which way the deformation is going to go, depends on the material. All right, so very simple equation, you know, probably, it's probably the longest you've stared at Hooke's law for any during your classes, but you know, there is a lot of generalizations that we can draw from this. And these kind of generalizations kind of form the basis. And one other very, very important part of this equation here that I actually don't mention in my notes, but it's probably the most important quality is that this equation is linear. And what I mean by linear is that the relationship between the external effects and the response is a purely linear equation. So you don't have any quadratics, no square roots, no weird exponents, anything like that. All right. Any questions on this? Okay. All right. And so so this is great, right? So we have kind of this simple equation, and we talked about how it generalizes, at least intuitively, at least physically. Now let's generalize it mathematically as well, because this is kind of what I call kind of a single degree of freedom system. And so you have essentially one unknown in this equation, which is just the displacement. Okay. So ideally, you know, what I mean by that is if you have a single spring, and you apply a force to it, and you know the spring constant, and you know the force that you're applying, you know, you only have to solve for one unknown. But when you're doing finite elements, you know, you are solving for lots of different unknowns at the same time. Okay? And so you're solving for, you know, just say for instance, let's say you have a mesh of finite elements, you're solving for the deformation at every location in that mesh, or every node in that. Okay? And so we need to be able to kind of generalize this mathematically to handle that kind of situation. Because even for a single spring, and so, you know, if we have a single spring here, we kind of innately simplified this above because we fixed one side of the spring, right? So we said the left side of the spring was fixed to a wall. But if we have kind of a general situation where we don't have that assumption, you know, technically both sides of the spring can displace. D1 here, D2 here. Okay. And so maybe the left side of the spring is displacing by amount D1, right side of the spring is displacing by amount D2. Okay. And then causing this deformation, we may also have different forces at every end of the spring as well. So let's say that we have an applied force F1 that side and an applied force F2 on the other side. Spring still has the same spring. Okay. And so let me go ahead and write out Hooke's law again. Right, so our good old Hooke's law is F is equal to KD. Okay, so how can we generalize this mathematically? And so instead of having just a single deformation and a single force, we have multiple forces here. Okay. But they're all still part of the same spring. So the way that we can kind of relate these is to change, instead of a force being our scalar and our displacement being a scalar, let's turn those into vectors. Where this force vector here, maybe equal to F1, F2. This D vector here is also a vector, so D1, D2. Okay. Where if we use column vectors here, this is a 2 by 1 vector, 2 by 1. And so that means mathematically, so if F is a vector, if D is a vector, that means K here must turn into a matrix. And in fact, the K matrix here, in order for this to mathematically work, we get the dimensions of all the vectors to match up. It must be a 2 by 2 matrix. If you take a 2 by 2 matrix and you multiply it by a column vector to a 2 by 1, then the result of that is going to be a 2 by 1. And so this matrix here, okay, this matrix here that we obtained by kind of mathematically generalizing the spring constant, this here is our stiffness matrix. Any questions on this so far? Okay, and so if we connect these two ideas, and so if we connect kind of the physical intuition for what the spring constant represents, and kind of this mathematical description of the stiffness matrix, we can kind of, make the definition here. So the stiffness matrix it's hard to actually find an exact definition of the stiffness matrix, at least one that is kind of general, but this is kind of my best attempt. Okay. And so the way mathematically this is going to work is that each element, each element in your finite element mesh can be represented by a stiffness matrix. Okay. So that what that represents is the stiffness matrix represents material geometric properties of an element of a physical system. So what that means is that, you know, the entries in the element stiffness matrix, so I've left them kind of general for now, right? And so it's just K11, K12, K21, K22, okay? The entries of the element stiffness matrix are going to be comprised of the material and geometric properties of that system. So I want to emphasize that just because, you know, even though this class, we focus almost primarily on structural FEA, you can still use finite elements to solve other types of physics. So transfer, fluid mechanics, probably the most common ones. You can also do electromagnetism, okay? And so, you know, what's going to be different about those different, you know, settings is that, you know, the material properties are going to be different. And so instead of the structural material properties like the Young's block with the Poisson's ratio, you know, let's say if you're doing heat transfer, you might see things like the thermal conductivity, you might see things like convection coefficients, you might see things like thermal diffusivity, heat capacity, things like that. Okay. And so, you know, this method here, even though, you know, focusing mostly on structural, it can apply to other things. Okay. And so with that said, you know, let's actually see how we actually derive the element stiffness. And so throughout the you know, throughout the next few weeks, we're going to go over different element types within the stiffness method. So we're going to start with springs, just because springs are the one. Then we'll go over truss elements and beam elements and see how they all. Okay. So let's go over the element stiffness matrix by spring. I'm going to go ahead and start by writing down our matrix system. F1, F2, 2, A11, A21, A2, sorry. A, multiplied by D1, D2. Again, you know, these represents kind of mathematically something like a single string. You know, maybe we're applying two forces, so we have F1 on the left, F2 on the right. And then we have the corresponding deformation D1 and D2. Okay. And so the question we're trying to answer now is that if when we have a system like this, you know, what do we put inside the element stiffness? Right now, those are just kind of generic. So we've put this system in kind of its matrix form, right? But also remember that, you know, in a matrix or a matrix system like this also represents a linear system of equations. And so if we go across the first row of that matrix, and so the first row, we're going to multiply that matrix by the vector. So we have F1, K2, K11, B1, second equation here is we have F2 is equal to A21 times D1 plus A22 times D2. So this is going to help us. And so if we were to form, if we could form kind of two linear systems of equations that relate, the forces to the deformations, then we can find out what those constants are going. Okay. And so to find this, let's look at kind of a specialized case or a special case of the spring. So let's look at a case for when we have a spring in equilibrium. So we have kind of equal and opposite forces on both sides. So a spring in equilibrium. This, so we have force applied on that side, so we'll call that T. We have force applied that way, that's T. Okay. And so even though this overall spring is in equilibrium, right? So there's a zero net force on the spring. We know that if we take a spring and we pull it from both sides, it's going to deform. And so we know that in response to this, these forces, the left node here is going to be pulled to the left. Okay, so we're going to have the D1 going in that direction. Right node will be pulled to the right. So other okay. So just so we have a point of reference, let's say that the positive x direction is going to the right. Okay. Just because we're going to throw some negatives into this. And so if we were to write, if we were to use Hooke's law on this to relate the tension and the deformation. So the amount of force that's being applied on the spring is a tension T, okay? So the force on the left-hand side is going to be T, okay? On the right-hand side, we're going to have the spring constant, so we're going to assume we know the spring constant for the spring is K, okay? And then we're going to multiply this by D, where this D here represents the total deformation of the spring. Except, what's going to be different in this case is how we define that total deformation. And so if you look back at kind of the first spring that we looked at today, one of the ends of the spring was fixed to the wall, right? That left side of the spring was not okay. Here we have a situation where both sides of the spring are going to be moved. And so the way that we can kind of represent that is that instead of total deformation, we can say that this is the difference E2 minus D. Okay. Because we know D2 is going to the right, D1 is going to the left. And so if we subtract those, then that's going to be the total deformation. So that's kind of our governing equation for this system. So we have the tension is equal to K times D2. Okay. So now let's take the situation, okay, where we have a spring in equilibrium, and let's apply that to our general framework, or general. So actually, let me go ahead and scroll up here. Try to get both in the same frame here. Okay, so our general spring here is at the top. And in particular, what I want to highlight here are the force values. So in our general spring, F1 represents the force that we're applying on the left side of the spring, or the first node, and F2 represents the force that we're applying on the other side of the spring, the right side. Okay. And so if we compare that to our situation here, T is equal to F1, except T is going in the opposite direction of F1. The way we drew F1 in the first figure there was going to the right, but the tension that we drew in the second figure means T is going to the right. Okay. And so mathematically, what we can say is that this is equal to, for F1, is equal to minus T. Okay. And then if we look at F2, F2 is defined going to the right, and the tensile force on the right side of the spring on the bottom is also. So we have T F2 positive T. Any questions on how I got those last two equations there? It's based kind of purely on kind of how we drew kind of the original kind of general spring and kind of the spring at the. There's only a difference in a minus sign between the two. That minus sign is there going to be. Okay. So now we have these two equations for F1, F2. So this is really good. Okay. And if you'll notice, you know, the reason I'm doing this is because if you look at kind of our general system here, right? This general system is telling us we need an equation for F1 and we need an equation for F2. Okay, so we're getting pretty close to what our general system requires. Okay, so let's plug in for T. And so if we have an expression for T, we've got it up here. Okay. Now let's plug in that expression for T into our equations. So if we have F1 here is equal to minus T. Okay. P2 plus P1. Okay. Let me go ahead and distribute the negative into that equation. Negative, we have F1 equal to K. 2. Let's do the same on the other equation. So we have F2 is equal to T. So we plug in for T, we have F2 is equal to K times D2 minus D1. Next thing I'm going to do is I'm going to distribute the K into the parentheses, and then let's also kind of show these two equations on top of each other. Put it in matrix form. To do that, we have F1 is equal to K D1 minus K2. Okay. We have F2 is equal to minus K D1 plus K D2. Okay. So let's take these two equations now and then let's represent them in matrix form. So in matrix form, we have F1 and F2 as a vector. Okay. We also have D1, D2 out here. Okay. And then in the middle, we have our element stiffness matrix. Okay, so let's go ahead and just pluck the coefficients out of this expression. So we do that, we get a positive K in the top left, minus K in the top right, minus K in the bottom left, and positive K in the bottom right. here it should be pretty clear. So now that we have it in this form, go ahead and circle this matrix that's in between, okay? And so this matrix right here is the element stiffness matrix of a spring element. So now that we have the element stiffness matrix of a spring element, we can then start to use spring elements in our stiffness method. All right, any questions on these steps here? Okay. All right, good. So we know how to deal with kind of a single element now. So if we have a single spring, you know, we can relate kind of the forces at two ends of the spring to the deformations using this element stiffness. Okay. Mathematically, it's actually very simple too. So we just have one spring constant and we just kind of populate this 2x2 matrix. Now let's look at a situation where we have multiple elements interacting with each other. Okay. So this is almost always going to be the case when you run any kind of FBA simulation. And so if you think back to all of our ANSYS activities, right? And after we did our mesh contained anywhere between, you know, maybe 1,000 elements to, you know, 50,000. Okay. And so learning how to kind of combine different elements together into one solution is a key step in the FBA. So it's so this step is called the assembly of a multi. All right. And so to illustrate this process, let's do kind of a very simple example here. So let's consider an assembly of two springs kind of connected end to end in series. All right, so on one end of this assembly, we're going to have a fixed wall. Let's have one spring connected like that. Let's have another spring connected like that. Okay. Let's assume, or let's not make any assumptions on a spring constant. So we can assume that the first spring has a spring constant of Ka. The second spring has a spring constant of Kb. Okay. So we're giving this system the freedom to have different spring constants. So you're going to see it's not going to affect our calculation. And so let's also label the nodes in this system. Node in a multi-element system here, a node basically just connects two elements together. Okay. It also connects the boundaries too. And so we're going to have one node here at the wall. The node 1 is going to be the node that connects spring A to the wall. Node 2 is going to be the node between Ka and Kb. Okay, so that's elements. And then node 3 is going to be the node at the very end. And then to stimulate the system, to basically to get a physical response, we need to apply some kind of external force. And so let's go ahead and put a tensile force on node. So we're going to pull node 3 to the right with the force. Okay, and so doing so, it's going to cause the system to respond. Right? So the way that we can kind of tabulate the response of the system is to kind of describe it in terms of the nodes. Okay. And so if we say that node 1 is going to displace to the right by an amount d1, we could say that node 2 is going to displace to the right by an amount d2. We could say that node 3 is going to displace to the right by an amount of d. Okay. I know I said node 1 is fixed to the wall. And so d1 in fact is going to be 0. But we're going to apply that later when we do the bound. Now, we'll leave the system general and we'll say that, D1 represents deformation. Okay. And so knowing this, let's go ahead and write out the element stiffness for both of these spring elements. So let's look at element A first. Element A has a spring constant of AA. Okay. And we can see from the figure here that element A is connected to nodes 1 and 2. That's going to be really important because once we assemble all the element stiffness matrices, we need to keep track of which nodes each element is connected to. Okay, so element A connected to nodes 1 and 2. Okay, and so if we were to write out the element stiffness matrix for this, we have F1, F2, F2. We have a spring constant of Ka, so we have Ka minus Ka minus Ka. That's going to be multiplied by the deformation vector d1, d2. Now let's go ahead and do the same thing for element B. So element B has a spring constant of Kb, and we can see from the figure here that it's connected to nodes 2 and 3. And so that's going to slightly modify our element stiffness matrix for okay. Because since element B here relates nodes 2 and 3, we're going to represent that. So for our forcing vector on the left, it's going to be instead of F1, F2, F2, F3. Okay. Our element stiffness matrix here is going to be about the same, okay? With the exception of the K is going to be KB. KB, 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 positive KB. And the deformations are going to be D2 and so small difference based on the nodes, but that's you're going to see in a second that's going to be something that's really, really important. All right, and so we have our two element system here, and so what we've done is we've taken each element, we've observed that each element there is a spring, and so we can write, and so we basically wrote out the element stiffness matrices. Any questions on this so far? Okay. All right, so this is good. So this is definitely a great start to the analysis. Okay. The problem is, we can't solve anything just yet because even though we have the element stiffness matrices for both springs, right now they're kind of separate. Okay. And if they were separate, if they were part of separate systems, then solve them separately. But they're not, right? These two springs are connected together at node 2. Okay. And so what we need to do from here is we take these two element stiffness matrices and basically combine their effects into one global system. Okay. And the idea is that, this combination procedure of taking the element stiffness matrices and combining them. The goal is to get kind of one big kind of matrix system of equations that we can solve all together for all of them. Okay, so let's see what that looks like. And so instead of two separate systems, F1, F2, and F3, let's have kind of one big system here. We have F1, F2, F3. We have a big matrix here. And then our response vector is going to be D1, D2, D. And so this kind of blank matrix that I've drawn in the middle here, this is our global stiffness matrix, which in this case is going to be a 3 by 3. The exact size of the global stiffness matrix, depending on how many nodes and how many elements you have in the system. But for this simple one, we just have it. All right. And so our next objective now is to see, how do we how do we compute this global stiffness matrix? Similar to what we had for the springs earlier, but now we actually have the element stiffness matrix for the springs. Now it's just kind of filling. All right. So the good news is that we've kind of already done the hard work in terms of determining the element stiffness matrix for a spring. Okay. And so the assembly step is basically just taking all of your element stiffness matrices and slotting them into the correct places. Kind of a long description there, but you'll see that this process is a lot simpler than this is probably the most fun part. Like almost like FEA Tetris. So we have our 3 by 3 system here. Okay. Our 3 by 3 global stiffness matrix, and we have two elements. Each of those elements has a 2 by 2 element stiffness. Let me do this, and so to kind of aid us in kind of making sure we put things in the right spots, let me go ahead and label the columns. And so the nice thing about the matrix form here is that the displacement vector on the right, 1, 3, it kind of essentially labels the rows. First row is going to be the D1 row, second row is going to be the D2 row, third row is the D3 row. Okay. Let me label the columns as well. So first column is going to be D1 column, second column is going to be D2, third column is going to be D3. Okay. And so we're going to use kind of these almost like coordinates in the. And so kind of the criteria or kind of the way that we put things in the right spot is that each element stiffness matrix needs to go in the spot that corresponds to the nodes that it. So that's why it's really important to kind of take note in terms of which nodes each element is. Okay, so let's see what that looks like. And so we have element A, we have two elements here. So actually I'm going to color code it. So element A we know is connected to nodes 1 and 2. And so let's find all the locations in our global stiffness matrix that correspond to nodes 1 and 2, using the labels for the rows and columns of each. Okay. And so we know that D1, D2, those correspond to the displacement of 2. So that's going to be the first two columns of the global stiffness system. And we also know that the first two rows of the global stiffness system correspond to nodes 1 and 2. Okay. And so you can draw a box like this. And so that pink box that I drew there corresponds to all the entries in the global stiffness system that act on nodes 1 and 2. And if you look at the size of this box, you can see that it's a 2 by 2 box, right? So it's two entries wide, 2 entries tall. If we look at our element stiffness matrix for element A, that's perfect, right? So our element stiffness matrix for element A is also 2 by 2. Okay. So that basically, so hopefully you can see here that we can basically take this element stiffness matrix and just insert it into this slot. Right? Okay. Let's go ahead and fill in those entries. A, 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 okay. Use a different color. Okay. Whereas element B is going to affect nodes 2 and 3. So again, we're going to look and see, all the columns and the nodes that are, or columns and rows that are affected by. So just like before, I'm going to draw a box around this. And so if I draw a box around the D2 row and the D2 columns together, then we get the following. Okay, so just like before, I'm gonna fill in the entries for this. Okay, and so I'm gonna leave the top left alone for a second. Put in minus KB, positive KB. And then we have one spot of this element stiffness matrix that overlaps a spot from the other. Okay. And so the question now is, what happens when we have overlapping parts? Because that's going to happen a lot. And so when you have overlapping parts, all you do is you just simply add, the entries that overlap. Okay. And so we have the top left entry of element B's element stiffness matrix and the bottom right entry of element A's element stiffness matrix. Those overlap. And so in that overlap spot, we're going to have the sum Ka and Kb, so Ka plus Kb. Okay. So that's great. So we've inserted our two element stiffness matrices. But you're probably thinking, we still have some spots that are unfilled, right? What about the top right entry of this global stiffness system and the bottom left? We have nothing there. And so when you have parts of your global stiffness system that are part of any element stiffness matrix, you just put a 0 there. Any questions on this so far? Yeah.
Single dimension, right?
Yeah.
Matrix would just get way bigger if we were going like a 2.
Oh, of course, yeah,
You add two extra elements to every.
exactly. So we are gonna do 2D problems with the direct stiffness method. So that's gonna basically double everything. So instead of a 2x2 element stiffness matrix, you still have a 4x4, which doesn't sound like that much, but yeah,
The
it's
matrix looks huge.
exactly, it blows up very, very quickly, and so, yeah, it does get out. So, for that reason, you know, when we're doing these problems, we're gonna restrict ourselves to just 2Ds as far as we can go. But yeah, you're right, it gets out of control very quickly. That's what,
Different health, like.
exactly, yeah. Yeah, so it's, so in those cases, you have to rely on a computer to. There's limitations to how much we can do right now. Any other questions on this here? Okay, so let me just kind of summarize those last two steps, put it in writing, just so you have it in your notes. And so we have entries overlap, all you do is just simply add those entries together. The other thing that we discuss is that whenever you have an empty spot, so any spot in the global system that's not covered by an element stiffness matrix, we simply just make those 0. And as we get kind of bigger and bigger systems, you'll see that the amount of zeros in our system grow a lot. That's fine, and so that's very typical. And in fact, you know, having a 0 in your global stiffness matrix is actually symbolic of something screwed up. And so if we look back at our global stiffness matrix here, we have kind of two entries here that have a 0. But they kind of represent the same thing. And so we have a 0 in the D1, D3 slot, and 0 in the D1, D3 slot. And so that's significant because if you look at our original system here, right, node 1 and node 3 are not directly connected, right? And so, you know, they're connected in the overall system, but they don't have they don't really share an element together. And so whenever you get a 0 in your global stiffness system, all that means is that those two nodes do not share an element together. Directly connected. That's going to be a nice kind of sanity check, because as we kind of do more and more complex direct stiffness problems, you know, it's always good to kind of sanity check your results. You know, we're soon going to have matrices. You know, this one's only 3x3. This is a very, very kind of a baby's first direct stiffness problem. We're gonna have matrices that are going to be like 16x16, 20x20, and so you're going to have, like, you know, dozens of zeros in those matrices. So, you know, you want to make sure that your zeros are going. All right, one last thing that I'll comment on here is that, you know, when you're inserting element stiffness matrices, they don't have to go in together as one. And so for a very quick example, let's say that we have an element. And just based on the numbering from our mesh, let's say that's connected to nodes 1 and 4. Okay? 1 and 3. And so if we assemble our system, you can see that node 1 and node 3 are kind of separated from each other in the global system. Okay? And so when we insert this this element stiffness matrix, it's going to go and use force mod. This would be Ka, Kc, minus Kc, minus Kc, and positive Ks. Okay. So sometimes that can happen, and in fact, you know, in the homework assignment that we're going to do on this eventually, this is going to happen quite. So you know, you don't have to keep them all together. You know, they may have to be separated in some circumstances, which is totally fine. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all I got for today. And so on Thursday, when we pick this up, we'll talk about boundary conditions and how we can apply those on our global system. Okay. And so what you're going to see is that it's going to modify our global. All right, and so remember, so activity 4 is due next week. So if you're having issues with it, let me know. And I'll post that lecture from last Thursday as well. So for those of you who are having trouble, you know, maybe looking at. Okay, so thank you guys for coming today. I hope you guys enjoy the rest of your evening, and I will see you all on Tuesday.
Part of the thing we have to make a graph with the number of elements.
Did you say like this is result?
How do you, I didn't. How do they? How do we check how many like right has?
So you're gonna click on mesh right here with the template, and then on the bottom left right here, like
Continuously. You're skipping the second.
yeah, I don't know, to make it smaller, you can make the element bigger than the so that's 0.3 feet. We can make it.
I think the other notes are pretty, like, I think it's using.
I want to make it. Right, I want to make it smaller, right?
Right, yeah, making it smaller will make the element number of elements.
Yeah. I remember like the very, I don't know. I don't know, but like at the very end, now you know how it's called.
So
Yeah,
it's kind of like the, so I think probably it's just probably the PDF.
So like.
Yes, and so in order to kind of fix that, what you do is instead of I would just do fix the point below there.
That's what I originally did, and then it still did that, so I put displacement to follow with the.
Let me see,
You know, written, that's not written, but like, you know, it's not gonna be able to do. I think part of the, I think it's part of like the midterm. It's not like.
I was like zoning out. I was just ready. My head is full and my tummy's empty.
I'm gonna try chat. Go ahead and play.
Let's make it like, be 1 hour.
You got preparations right now? It's less much to.
Oh, yeah, you were in the class.
You check it.
Yeah.
School does like.
Oh, okay, yeah, so it's. That one. Okay. Good, let's try it. Sometimes it can do weird.
Still doing it, but now on this side.
It almost kind of looks like. See you here. Okay, I know. So these two connections here. And so when you're connecting the left side of the road and the right side of the road to the grid, it's not the entire road that you're connecting, it's just the edge. Just the edge of the road that's connected. So this part's correct, so you should have the entire bridge phase. But then this one down here should be the edge.
That would be the blue one?
Yeah, the blue.
We could give that a try and then.
Doing stress analysis.
As long as we can model for it, it should be. I think the thing that's difficult for 3D printed models is that your material properties are going to be anisotropic.
Yeah,
And so it's going to be weaker in the just whatever.
like against the grain.
Exactly, against the grain. So you have to do. I would do an orthotropic material. That probably makes more sense. Because then what you can do is you can apply less strength to that.
Yeah,
Is you know what the strength was the young project?
it's at G is a material, I'm not sure, I'm gonna have to look into it,
Okay.
I was wondering, like, it's important, how do you even go about modeling it?
Yeah.
Are you able to do just the normal static structure?
Yeah, it would be static structural. The only thing that'd be different is that we have to.
Okay,
So I think
but it's non-isotropic.
Exactly, yeah. So I have a handout on it. Let me check and see which handout it is.
Like further, the final project, I mean, I'm in my senior design project at